I hope the other okay, so we're going to start recording now. High definition or not high definition? Oh, no, that didn't work. Okay. We're going to start recording now anyway. Okay, record to the cloud. Right, and I have to start there's too much technology going on these days. I have to start the timer because the camera, the high definition camera, will only record for 30 minutes. Okay, I can try that. But today we talk about, right, good. We're recording? Yes, we're recording with that camera, everything is good. So now we're actually going to talk about a particular problem, which is not just, some weird abstract problem. It's a concrete problem. It's a concrete problem for you because it's actually your first homework assignment. Your first homework assignment is not like the other homework assignments because it's only one question, and it's hard, but it's not super hard, and it's there to because I'm supposed to give you something back back before the drop date. So the idea is there will be a tutorial on Friday, which will be sort of how to do this stuff, and then it'll be due a week from Friday, so I think on the 14th at midnight. So next week there will be 2 office hours on there'll be 2 office hours, I think, on Thursday and Friday. But the tutorial this week is for this homework. The tutorial next week will be for the homework that's due the week after. So please don't go to the tutorial and say, I left this at the last minute, I can't do the homework, because the office hours are for that. So let's talk about, what's this problem we're going to talk about today? So it's going to be sort of a flow from the stuff we were talking about on Monday, that was only 2 days ago, which was hard versus easy, or well, impossible versus impossible. We sort of discussed that. Then we got into this hard versus easy stuff. And I told you that one of these problems that I gave you some examples of problems that are Eulerian cycle is easy, and Hamiltonian cycle we think is hard. We don't have a polynomial time algorithm for it, and we've been looking for almost hundreds of years. And there are lots of other problems which turn out to be equivalent to Hamiltonian cycle. Okay, so we're going to see a bit more of that today, but we're also going to start getting into this first paradigm of algorithm design, which is divide and conquer. Most people in most classes, when I saw divide and conquer, they were like, oh, merge sort, quick sort. And it's like people think, oh, this is super easy. You use divide and conquer for easy problems. Well, so in order for you not to think that, I'm going to teach you divide and conquer on this insanely hard problem, which I've told you we don't have a polynomial time algorithm for, and actually what I'm going to teach you is not polynomial time. It's just going to work really, really quickly in practice. And then we're going to get into some details. Okay, so where did this problem come from? Well, so let's go back into sort of the history of graph coloring. So we said that the graph theory started with Königsberg. By the way, I remember I asked you to remind me about exclaves. So Königsberg is now Kaliningrad. It's an exclave of Russia. So this will come up in just a minute. I've looked at A1. This is having requirements on the running time of the code. No, but if you do it brute force, it won't stop in your lifetime. So I'm going to show you 2 versions for coloring Nova Scotia. Now, you can brute force Nova Scotia. right? Like it's only 18 counties. So you can, and so if you try all the possible, okay, we'll get into it. If you try all the possible 3 colorings, it's 3 to the 18, that's not actually very much. It's like 400 million or something. Your computer will just burn through it. The map on the assignment has 42 regions. If you try to 4-color and you try all the possibilities, it's 4 to the 42, it's like 10 to the 26, 10 to the 25, something like that. So it's not going to stop soon. So you can't just use the super simple, like try everything. You have to at least be a little bit sneaky. Okay, so graph theory got started, and then so it was in, I just checked the dates, but I forget. It was like in the 1800s, in I think 1854 or something like that. He was actually also a mathematician. This guy, Francis Guthrie, I think, wrote to his brother, who's like Frederick Guthrie or something like that, who was studying with De Morgan, who is, if you studied De Morgan's laws in propositional logic, this is Auguste de Morgan. And so he noted this thing. He said, I just noticed I can color all the counties of England, or, yeah, I think just of England, with 4 colors, such that no 2 that share a border of positive length, which means they can touch at a corner, because a corner actually has 0 length, right? It's just a point. But a line has positive length. So if they share if they share a border, they can't be the same color. He said, I can color with only 4 colors. So the same, I remember, like when we were children in geography class, we had to color maps. And actually, I remember reading in a book, somebody observed, like, yeah, up until about like high school, that's mostly what your geography mark was, how neatly you could color the map. I could color fairly neatly, but I always lost my pencil crayons. So it would have actually been really useful to me to have a good algorithm to give me a 4 coloring, because then I would only have needed 4 different colors. Except you need, like, they have these silly rules, like blue for water. Okay, so he said, like, is this a coincidence, or can you always do this? So looking at the counties of England, you'd think, yeah, that doesn't seem to be just a coincidence. There were 39 counties back then. They've been merged since then. There was a conjecture that got published twice, once by, they're not sure which brother, because they both have the same initial, and so it was just listed as F. Guthrie. And then it was published again by De Morgan in like 1860, I think. And the conjecture is, yes, you can always color a planar map, and it doesn't actually, like, if it's on a sphere, you can always project it on a plane. You can color a planar map with 4 colors. Now, this exclave thing gets a bit complicated, because an exclave of a country is a part that doesn't have to be connected, and you can fairly easily come up with examples. If you're allowed to have exclaves in your map, and the exclaves have to be the same color as the country, then it doesn't work. So I'm not going to use the new markers yet, because you should be able to see this. Because, right, so if we have, let me think. So this is my map. And so this is country A, B, C, D, E, A. Can you read that? I hope. I can read that on my screen. Yes, okay. So I claim that this cannot be 4-colored, right? So this is an exclave of country A. And the reason this cannot be 4-colored is C, D, and E are all different colors, are all adjacent to each other, so they have to be different colors, right? So these have to be different colors. B is adjacent to all of these. And so it has to be a different color. So you need 4 colors for B, C, D, E, but then A is adjacent to B and C, D, E, right? So now you need 5 colors. Okay. So if you're allowed to have exclaves, then things get complicated. Now, exclaves, it sounds like Kaliningrad is an exclave. It's Kaliningrad Oblast. So then you have like so for example, there's an exclave of Italy in Switzerland. There's an exclave of Spain in France. There's where. Like their overseas territories. So I was thinking of making a color the world map, but then I got it. So for example, like French overseas departments are actually considered part of France. So close to us, it's not exactly an exclave, but if anybody's been to Saint-Pierre-et-Miquelon, it's like a few hundred kilometers northwest of us, I guess. Uh-oh, the audio is important. So yeah, Saint-Pierre-et-Miquelon. I went there. There was a conference in Newfoundland. I was living in South America, and it has the same plugs as Europe. So I went from the conference in Newfoundland. I spent a few days on Saint-Pierre-et-Miquelon, so I could charge my razor. But everybody, there's an exclave which is really big, which we don't usually think of it as an exclave, which everybody shouldn't. So just to make sure that people are awake, tell me the biggest exclave you can think of. Yes, Alaska. So this is, I've never actually, until I was preparing this lecture, I'd never actually heard of Alaska referred to as an exclave, but I think it is. Okay, so wait, somebody else had an, yes. Okay, so we're going to ignore exclaves. So there was this conjecture, and it ended up being sort of a key part of graph theory. Now, why is it graph theory? Because it turns out if you take I shouldn't have just erased that. If you take a map and you draw a vertex on each region of the map, and you draw an edge between 2 vertices if they share a positive length border, then the map can be k-colored if and only if the graph can be k-colored if and only if the map can be k-colored. Where the graph coloring says, if 2 vertices share an edge, then they can't be the same color. Now, if for every place that the regions touch, you draw an edge through that connection, then you get a multigraph. So vertices can be connected. 2 vertices can be connected with multiple lines. So, for example, let's not talk about. Okay, so in this example, if I had A, B, and C, then A would actually, the corresponding multigraph would be A connects to B twice. Okay, so it turns out that actually if you do this multigraph thing, then you get what's called the dual of the map, right? So then the graph and the map are duals from the map you can get the graph, and from the graph you can get sort of the map, in that it's up to topological equivalence. So it is like, you obviously can't get like all the squiggly lines, but up to like, do people know what topological equivalence is? Like if you drew it on a rubber sheet, you could, okay, somebody does. Okay, good. So this isn't so important for us, because we just care that if you can k-color the graph, the map, you can k-color, if and only if you can k-color the map, you can k-color the graph. And you don't need this multiple edges thing. It's not going to be important. This is algorithms, it's not topology. So So this theorem, this conjecture hung around for quite a while. So I think around the end of the 1800s, he would prove the 5-color theorem, that any planar map, without escalates or whatever, any planar graph, a graph is planar if it can be drawn in the plane such that the edges don't cross. It doesn't, not all graphs are planar, and not all the drawings of a planar graph have to be planar. You can definitely make the edges cross if you want. So it turns out they're doing some construction and they have air horns. I don't know if you can hear that. I hope not. They're also like cutting down a tree and running it through a chipper. So it turns out like when you do graph theory, there's this graphs are planar if and only if they don't contain a K5 or K33 as a minor. So this, we don't need this. So we do need to know if a graph is planar if it can be drawn in the plane such that the edges don't cross. Not all graphs are planar, but planar maps correspond to planar graphs. Okay. So anyway, this theorem hung around for a while, and it was eventually proven by Appel and Haken, I think in the 60s or 70s at University of Illinois. How can I forget? I stayed up late doing the homework. You can probably see when it got posted. Illinois Urbana-Champaign. Yeah. I was thinking, I can't believe, like, my brain just shut down. I was like, University of Illinois, University of Indiana, University of something starting with that. But yeah, of course it's Illinois. I think. Now actually this is kind of cool because Haken, so part of the proof was checked by his daughter, who is Dorothea Haken. And she comes up again in this course because she was one of the co-authors of the master theorem. And also she taught me third-year algorithms. So like a couple of decades ago when I was where you are now, except I was actually in a classroom. Then I was, except she was Dorothea Blostein by then. Okay, so, I got this out of order. I was talking about maps and graphs. Okay, so they proved it, and this was the first time people proved something big using a computer to run through lots of cases. I think it was 1,800 and something cases, 34 cases. And so they proved it exhaustively, and a lot of mathematicians were unhappy because they said, like, we can't actually check your proof manually, we don't really understand it, is this really a proof? Okay, so let's talk about, okay, if I give you a graph, if I give you a planar graph and I ask you if it's 7-colorable, what do you say? Hands up, everyone who thinks you say yes. Okay, if I give you okay, so I should check the participants. If I give you 60 attendees, I paid for like the 500 attendee Zoom subscription. Because, okay, yes, so at least some people think you say yes. Okay, so if I give you a graph, if I give you a planar graph, now there are polynomial time algorithms to check whether a graph is planar or not. So I give you a planar graph and I ask you, is this 7-colorable? Like, can you color it such that each vertex is assigned one of 7 colors and no edge has 2 endpoints the same color? An idea? Well, you say, I told you that the, yes, okay. So I just told you that you can 4-color. There's a 4-color theorem. And actually this, I will try to find the picture again. I'm trying to learn Czech on Duolingo, and one of the things was 4 colors that are definitely enough. 4 barvy úplně stačí. And so this makes it into Duolingo. So if 4 colors are enough, 7 colors are definitely enough. So if I tell you the graph is planar, then and I ask you if it's 7 colorable, you say yes. If I ask you if it's yes, a 4 coloring is the 7 coloring. You just ignore some of the colors. Now, clearly, there are for any number of colors. If I don't tell you the graph is planar, there are graphs which require any number of colors up to the size of the graph. Because, for example, a clique where every pair is connected. So a 4 clique is planar, but a 5 clique isn't. So, for example, an 8 clique requires 8 colors. So, if I give you a planar graph and I say, is this 7 colorable? You say yes. If I say 6 colorable, yes. 5 colorable, yes. 4 colorable, yes. Now, what if I ask you is it 1 colorable? So there is an easy condition for if it's 1 colorable. I'm going to turn on the chat and see if anybody writes this. No, wait. So the theorem is the map is 4 colorable if it is planar graph. Yes, if it's planar graph is 4 colorable. Yes. So yes, only if there are no edges. Yes. Okay. If I give you a graph and I ask you is it 1 colorable, if it's an independent set, so all the vertices are isolated, then the answer is yes. You can color them all the same color. So now let's talk about this. So what if I ask you if it's 2 colorable? So I'm going to keep my new markers here for moral support. So if I say, okay, let's see. Okay, is this graph 2 colorable? How do we tell? Well, we start and let's say we start here and we say this is red. So all of its neighbors had better be blue. And then all of their neighbors had better be red. And then we get a problem because we say, and all of their neighbors had better be blue, but they're not. Some of them are red. So we get a problem. So this is basically just breadth first search. Maps, planar maps, yes. If you don't have like bridges and tunnels, so yes, if they're planar, no bridges and tunnels, then you can do this thing where you draw the vertex in each region and draw the lines, and those lines won't have to cross. So yes, the corresponding graph will be planar. So basically, you do this breadth first search. And either you get a 2 coloring or you find an odd cycle, right? Because this is 1, 2, 3, 4, 5 vertices, right? And so you can't color an odd cycle, which is like a triangle or something. You can't color it with 2 colors. So if I ask you about 4 or more, the answer is easy. You just say yes. If I ask you about 1, the answer is also easy. You say yes if and only if it's an independent set. If I ask you about 2, you actually have to do a little bit of work. but not a lot. Now let's talk about 3. They want adjacency to, yes. Oh, yes. Somebody noticed that I made a mistake on the adjacency list. Possibly I made more mistakes. I will check and see if this is the same mistake that somebody emailed me about this morning. It didn't actually affect my checking the solution. I don't really care how many colorings that map has. I just actually want people to try it and get some feedback and sort of get a feeling for what this course is. It's not going to involve that much coding, the whole course. But I want you to have something which is like, okay. So I just have to check and see if this camera is going to stop. Okay, so let's talk about, we have 43 seconds. Okay, so 1 colorability, 2 colorability is easy. Let's talk about 3 colorability. So 3 colorability is one of those problems we don't have a solution for, not even on planar graphs. We don't know how to do this in polynomial time. Like obviously we can do it, but you can just check all of the possibilities, but that is slow. So we're going to talk about, so can you get any faster? Can you get something with polynomial time? Nobody's ever found an algorithm with polynomial time for general 3 colorability. Okay, so we're going to stop the